Hello everybody. So in the previous video, we went through the theory part related to trusses. Now let us start solving the problems related to trusses. So in all the problems related to trusses, you'll be finding two things. The first thing what you find will be support reactions, and also you'll be finding the force which runs through all the straight members. Force which runs through all the straight members. I'll just write it as force. So these are the two things which you will be finding: unknown force and support reaction. So in the previous case, in the case of beam, so we were finding only support reactions, but here you have two things to find. The first one is support reaction, the other one is force which runs through all the straight members. So as you know, as we discussed in the previous video, all the straight members carry certain amount of force, or certain amount of force transfers through all the straight members, and then it reaches the supports. So you have to find support reaction as well as you have to find the force which runs through all the straight members. So let us go through all the steps one by one. Step number one is to identify the type of support, mark the support reaction, and to find the support reaction. You'll be identifying, marking, and finding the support reaction. Step number one itself. For example, here this particular support is a hinge support, so it will offer two reactions. Let me consider this as A, B, and this as C. So this will be RAY, and this will be RAX. As you know, this is a roller support. So this will be RBY. So you have identified, you have marked. Now you have to find it in step number one itself. So you have to find support reaction in step number one itself. To find support reaction by applying three conditions of equilibrium: summation of Fx equal to 0, summation of Fy equal to 0, and the moment either about A or B equal to 0. A or B equal to 0. Finding support reaction is step number one. So in first step, you'll be identifying the support, type of support given, you'll be marking the support reaction, as well as you'll be finding the support reactions. This is all about step number one. Step number one is completely concerned with finding the support reaction. So you'll be finding the support reaction by applying the three conditions of equilibrium. Because the entire system is non-concurrent. You'll be considering the entire truss system. And step number two. So you will be assuming that all the straight members carry tensile force. You'll be assuming that all the straight members carry tensile force. And mark the tensile force. You'll be assuming that all the straight members carry tensile force, and you'll be marking them as well. So you know how to mark the tensile force. And if a particular straight member carries tensile force, it will always be directed away from the joints. This is one of the straight members. Mark the tensile force. Away. Let me mark this as FAB. Let me mark this as FBA. This is the other straight member. Away and away. Away from the joint and away from the joint. This is FBC and this is FCB. Again, this is one of the straight members. Away from the joint, away from the joint. This will be FCA. And this will be FAC. This is how you mark. Or this is how you assume that all the straight members carry tensile force, and you have to mark it. So if a particular straight member carries tensile force, when you find the tensile force in the next step, if you get a positive answer, then your assumption is right. If you get a negative answer, then it carries compressive load instead of tensile. As simple as that. So we'll assume that all the straight members carry tensile load. If our assumption is wrong, we'll get a negative answer. As simple as that. So in step number one, you'll be finding the support reaction by applying the three conditions of equilibrium, and in step number two, you'll be assuming that all the straight members carry tensile load and mark them. So you know how to mark the tensile load. Consider each straight member and mark the tensile force in such a way that it moves away from the joints. Away from the joint, 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 and away from the joint. In this. So this is all about step number two. It's very simple. Step number three is very important. In step number three, you'll be considering each joint separately. you'll be considering each joint separately, and draw the free body diagram for each joint. So here, when you draw the free body diagram, the system will be concurrent. So consider each joint, draw free body diagram for each joint, and apply two conditions of equilibrium. Why two conditions? Because you draw free body diagram, and in free body diagram, the system will be concurrent. So in step number 1, you'll be considering the entire truss. You'll be considering the entire truss. So when you consider the entire truss, the system will be non-concurrent, and hence you'll be applying 3 conditions. In step number 3, you'll be considering each joint. Each joint in the sense it goes in this while. Consider joint A now. I'll consider joint A. So just to draw joint A, let me consider this point as joint A. Mark all the forces associated with joint A. You have R, A, Y, you have R, A, X. Let me draw the coordinates first. R, A, Y, R, A, X, and you have F, A, B, and you have F, A, C. If this is theta. So all the forces are concurrent here. This is the free body diagram of joint A. So in this way, you have to consider joint C and joint D as well. Consider all the joints separately. Draw its free body diagram. We have already drawn the free body diagram. After drawing the free body diagram, it's concurrent. Now it's enough if you apply only 2 conditions of equilibrium: summation of Fx equal to 0 and summation of Fy equal to 0. In order to find the unknown force. Ultimately, we need FAC, which is equal to FCA. We need FAB, which is equal to FBA. We'll get these two just by applying the equilibrium condition to this particular free body diagram. So we need FBC, which is equal to FC. So we got the value of support reactions in step number 1, and we'll get the value of these forces which runs through all the straight members in step number 3. So in step number 2, you'll be assuming that all the straight members carry tensile load. And in step number 3, you'll consider each joint separately. You'll draw the free body diagram, and once you draw the free body diagram, it's enough if you apply only 2 conditions of equilibrium. This will be the example. This is the example free body diagram. So let me solve one problem here, and you can refer all other problems from the notes and solve. So let me consider problem number 1 from your notes. Let me share the screen and show you the problem. So these are the steps. Which we went through just now. And this is the first problem. Problem number 1. Find the forces in all members of a given truss. So we went through the steps now. We have 3 major steps. So step number 1 is to find the support reaction. Step number 2 is to assume that all the straight members carry tensile load. And in step number 3, you'll be considering each joint separately, and you'll be marking the support. You'll be applying 2 conditions of equilibrium in order to find the forces which runs through all the members. Let me just show you the way to solve this particular problem. So here you can mark all the tensile forces in the question, and you can indicate support reactions, etc. in the question itself. So it carries an external load of 100 Newton magnitude. At point C, and the distance is given. Distance between A and B is given as 6 meters. 3 and 3 meters. And the angle is given as 60 degrees. Yeah. Yes. So let us start solving the problem. I'll just help you with the problem here. So this is the given problem. So we'll follow the steps. One by one. So step number 1 is to identify the type of support, mark the support reaction, and then apply 3 conditions of equilibrium to find the support reaction. So this is a hinge supports. It offers 2 reactions, RAY and RAX. So this is a roller support. It offers only one reaction, so it will be R, B, Y. Now we have to find these two support reactions by considering the entire truss. So in order to find this, you have to apply all the three conditions of equilibrium. Let me apply the first condition of equilibrium. Summation of Fx equal to 0. So you just have one force in x direction, which is Rx, which is straight away equal to 0. Let me apply the second condition of equilibrium, which is summation of Fy equal to 0. Which is summation of Fy equal to 0. So you have two forces, Ray plus Rby minus 100 is equal to 0. You cannot solve this. Let me consider the equation number 1. Apply the third condition of equilibrium. Moment either about A or B is equal to 0. Moment about A, let me consider A as 0. Moment about A is equal to 0. So A is this particular point. So Rax and Ray will not produce any moment about A. Check whether this 100 Newton force produces clockwise or anti-clockwise moment about A. It will produce clockwise moment. So it is 100 into the perpendicular. This is the line of action, and perpendicular distance is this 100 into 3. And check whether RBY produces clockwise or anti-clockwise. It will produce anti-clockwise moment. So minus RBY into 6 is equal to 0. So therefore, you get the value of RBY. You get the value of RBY as 50 newtons. So if you substitute this in equation 1, you'll get the value of Ray as 15 newtons as well. 15 newtons as well. So it's a symmetrical truss. Truss is symmetrical. So 100 Newton is evenly distributed in between these two supports as 50 newtons and 50 newtons. So Ray is 50 newtons, RBY is 50 newtons, and Rax is 0. Rax is 0. So we got the support reactions. This is all about step number 1. Step number 1 will always be easy here because you'll not be given with the UDL or UVL or an inclined load. Nothing will be there. All the loads will be straight. Without any inclination. So you can easily find the support reaction in step number 1. So step number 1 is done. We got the support reactions. Now in step number 2, you'll be assuming that all the straight members carry. In step number 2, you'll be assuming that all the straight members carry tensile force. You'll be assuming that all the straight members carry tensile force, and you'll be marking that. Let me consider this straight member AB. So if AB carries tensile load, the force should be marked away from the joints. So A is the joint, B is the joint, away from the joint. This will be FAB. Away from the joint, FBA. Let me consider this member, AC. Away from the joint, FAC. Away from the joint, FCA. Let me consider this straight member. Away from the joint, FCB. Away from the joint, FBC. So we have assumed that all the straight members carry tensile load, and we have marked it as well. So this is all about step number 2. And in step number 3, you'll be considering all the joints or the required joints separately, individually, and you'll draw the free body diagram for that particular joint, and then you'll be applying. If you draw the free body diagram, then obviously the system will be concurrent. So since the system is concurrent, you'll be applying only 2 conditions of equilibrium. So let me consider joint A now. So when you consider joints, you have to remember that you'll be considering all the joints. If there are a number of joints in the given system, consider that particular joint with the least number of connections first. Consider that particular joint with the least number of connections first. So here, joint A has 2 connections, joint B has 2 connections, and joint C has 2 connections. So all the 3 joints have same number of connections, so you can consider any of the joints. But in a big truss, in a different problem, if you have more than 3 or 4 or 5 joints, you have to select that particular joint with the least number of connections. Connections are number of straight members coming and joining together. Least number of connections. So let me consider joint A here. So all the 3 joints have same number of connections. So let me consider joint A. Let me start with joint A. Let me draw the free body diagram of joint A, consider a particular point as A, draw the coordinates, and mark all the forces associated with A. So you have Ray, let me mark Ray here. Ray, which is equal to 50 newtons. We know the value. So we have Rax, which is 0, no need to mark it. You have FAC. Let me mark FAC here. FAC, we don't know, and this angle is 60 degree. And we have FAB. We don't know this. So you have 2 forces, FAB FAC and RAY. You can draw RAY in the negative y scale as well. Let me draw it here. It becomes easy for me to show the resolved components. So let me draw RAY here. RAY, which is equal to 50. So this is the free body diagram. This is the free body diagram of joint A. Now FAC is inclined. Now we have drawn the free body diagram and we have to apply the conditions of equilibrium. We have two conditions of equilibrium to apply. In order to apply two conditions of equilibrium, we have to resolve this inclined force into its horizontal and vertical components. Horizontal component will be FAC cos 60 and the vertical component will be FAC sin 60. FAC sin 60. Now let us apply the two conditions of equilibrium. The first condition of equilibrium is summation of Fx equal to 0. So you have a number of forces moving in x direction. FAC cos 60, FAC cos 60 plus FAB is equal to 0. Let this be equation number 1. Let this be equation number 1. So you cannot solve this. Apply the second condition of equilibrium. Only two conditions of equilibrium are to be applied here because it is a concurrent force system. Summation of Fy equal to 0. You have 50 Newton plus 50 it moves upwards plus F is C sin 60 is equal to 0. So you get the value of FAC as minus 57.73 newtons. What does this minus sign indicate? Minus sign indicates that FAC or FCA is not a tensile. Instead, it is a compressive load system. Because we have assumed that it is tensile, it's giving us a negative answer, and it indicates that it is not tensile, it is compressive. So just write C in the bracket just to differentiate. This is a compressive load, it's not tensile. We have assumed it to be tensile and our assumption is wrong, so it's giving us a negative answer. So we got the value of FAC now. FAC. Consider or substitute FAC as minus 57.73 in equation 1. Substitute FAC as minus 57.73. Don't change the sign, let it be minus. Even though our assumption is wrong, you have to keep it minus. In the bracket, you can mention it as compressive load. Minus 57.73 cos 60 plus FAB is equal to 0. So therefore, FAB is equal to, FAB will be a positive answer because this goes to the other side. So FAB is equal to 28.86. 28.86. Here our assumption is right. It is a positive answer, so it is tensile. Write T in the bracket. If you get a positive answer, write it as T. If you get a negative answer, mark it as C. Now we got the value of FAC. FAC is equal to FCA. So we got the tension through this particular tension or force through this particular straight member AC. So we got the value of FAB. FAB is equal to FBA. So we got the tension or force through this straight member as well. So we have three straight members. Out of these three straight members, we got the force through two of the straight members just by considering one of the joints. So now it's enough if you consider either B or C. No need to consider both. If you consider B, you'll straight away get the value of FBC. FBC is equal to FCB. So you'll get the force through this straight member BC now. B or C can be considered, either B or C. So let me consider joint B. Let me consider joint B. You can consider C as well, no issues. Let me consider joint B. I'll draw the free body diagram of joint B. So this is joint B. You have RBY, which is 15 meters. This is 15 meters. Mark this. This is FBA, which is equal to FAB. FBA is equal to FAB, and which the magnitude of this is 28.86 newtons. Magnitude of this is 28. It moves horizontal to the left, so its magnitude will be negative later when we apply the equilibrium condition. So FAB is done. Now you have FBC, which makes an angle of 60 degrees. We don't know the value of FBC. Resolve this into its horizontal and vertical components. Minus because it moves horizontal to the left. FBC, I write it in the bracket. Magnitude is FBC cos 60, and the vertical component is FBC sin 60. This is the free body diagram. You have to apply the two conditions of equilibrium. First condition is summation of Fx equal to 0. So just go through all the forces which moves in x direction. This is minus FBC cos 60 and minus 28 because this is moving horizontal to the left. This is moving horizontally to the left. So if we had minus here as well, so it would have been become minus and minus plus later in other problems we'll encounter such cases. So here it is minus 28.86. Minus 28.86 is this is equal to 0. So straight away we'll get the value of FBC. Straight away we'll get the value of FBC just by applying one of the conditions. Just by applying one of the conditions as 28.86. FBC is also equal to 28.86 and it is positive. It is positive in this case. No, not 28.86. 28.86 minus, plus 28.86 divided by cos. So cos 60 it will be, and negative sign will remain as it is. So it will be minus 57 point divided by this will be minus 57.72. So since it is minus, our assumption is wrong. It will be compressive. FBC is compressive. So we got FBC now. FBC is equal to FCB. So you got the tension through this straight member as well. So we got the tension through all the straight members, and also we got the support reaction. So this is how the numericals will go. So this is one of the example problems, and all of the problems will be solved exactly similar to this. You'll have a bigger truss. This is a very small truss. You'll have a number of other straight members and a number of joints. We just had 3 joints here. You'll have minimum of 8 to 10 joints in the problems. You can go through, and there are a number of solved examples in the notes. You can go through all the solved examples. All are similar to this. All the problems are very, very similar to this. Thank you.